Hello everyone. Today we are going to have our fifth tutorial that is based on analog to digital converters. So, in this tutorial, we are going to discuss about how to configure an ADC and how we can give some input to the ADC pin in the microprocessor, and we'll be reading those signals in the Code Composer Studio. Before we begin, we need two documents which were required for writing this code and understanding the basics about this ADC module. First one is that LAUNCHPad 379D user guide, from where there you can get all these pin informations like which ADC pin is assigned to which ADC input. And so these things you can read from here. And another is technical reference manual. In this chapter number 11 deals with analog to digital converter. So first a brief introduction to this ADC module block diagram. So as you can see here, there are 16 ADC input pins, and then this is sample and hold circuit, which is responsible for sampling the whatever input which you are giving through the ADC channel, and then a converter which will convert these analog signals into digital, and then the result will be given here, and then this post processing block, and then we can read these results. And along with that, you can see here is some SOC arbitration and control, signal mode and resolutions. So this signal mode basically help us to select in which mode do we want to operate the ADC input pin. Like for normal ADC input sensing purposes, we keep it in single-ended mode, and for this communication and all, this can be used in differential mode. And the resolution is also selected based on that. If it is used for normal sensing, it is in 12-bit mode, that is single-ended, and otherwise 16-bit, that is for differential. And these things are configured when we are configuring our SOC. SOC stands for start of conversion block. And after the conversion has been done, then end of conversion signal is generated. That end of conversion signal says that the conversion is now complete, and based on that, this signal is given to one interrupt block. This interrupt block will now inform this SOC again, like the conversion which was going on has been completed. Now we can again sample the next set of signals. So this is a brief introduction, and you can read on your own. Like there are various information like how to configure the clocks, like which control register do we need to configure, and so these all informations are here. So we'll start with the our tutorial. So as we can see here, so this is the basic outline of our this session. First, we'll see what are our objectives, then how we are going to configure our ADC that composes of this ADC power of sequence, SOC selection, EOC, and interrupt selection. Then after all this configuration, we need to start our conversion. So how to start the conversion in the ADC module, then reading the ADC result. So let's see what are our objectives. The first one is to configure and use the ADC module. And for the example, we have used the built-in 3.3 volt supply which is available in the board, and even the 0 volt signal which we can take from the board itself, and that we have given into one of the pins, ADC pins. Like here we have configured this pin number 70, and this we have read in the Code Composer Studio. If we are connecting into 3.3 volt or 0 volt, that we are reading in the Code Composer Studio. And we have considered SOC 5 as our SOC for this particular pin. And how we are going to configure it, we'll see in the subsequent slides. And one important thing is here, like please, if you're trying to do this, please don't connect the 5 volt pin is also there. Please don't connect. It will damage the board, because this is meant for only 0 to 3.3 volts. So moving forward, uh, when we are configuring our ADC, first we need to power up our ADC module. By default, it won't be on. We need to configure it, and then we need to power it on. So while powering up the ADC, the first step is there are 4 steps. So the first step is setting the clock bit. So set the bit enabled for the desired ADC clock. And here we have used peripheral clock gating register 13. Why 13? Because there are several peripheral clocks available, and this peripheral clock gating register 13 has been assigned for this ADC purpose. Various clocks are referred for different other purposes. So as you can see here, I have mentioned device register and this start address, because as we are going to do the coding in the assembly language, we need to give the information, all this information, like which particular mode we are going to use, which particular clock we are going to set. So these all information we need to give it in the register. So the start address we need to see. So in order to see this peripheral clock gating register, this comes under CPU system registers. So this we can, as we can see here, I'll show you. So here you can see this CPU system control based addresses. So CPU system register, the start address is this, and the peripheral clock gating register 13. If you want to see this, you can search exactly these acronyms which I have given, and you will be able to get like which is the start address, what is the offset. So in that CPU system registers, you can see here the peripheral clock gating register 13 has an offset of 3C. So the 3C is here. Now I'll show you the code. So in this configuration part, first what we are doing, we are doing using the index addressing mode, and first we are moving this 5D3C for setting this peripheral clock gating register 13 in this location. And now we need set this to 1. So as we'll see here, we go. It is a again 32-bit register. Why 1 here? See, as we have planned, we are using pin number 70, and in order to set this ADC A, we need to set this one to 1. So that's why we are moving 1 to ADC, enable the ADC A module. So now we have configured the clock as well as ADC A module. Now we'll go to the second step. In the second step, what we are going to do is setting the desired ADC clock divider P scale value, and we'll set the resolution and the signal mode, what will be the P scale value, all these things. As you can see here, signal mode, resolution are coming, and that you might have seen while I was referring to the ADC module block diagram. So first, as we are referring to this ADC A register, you can see here we have set ADC A register. So here you can access all the ADC registers from this section. So ADC register. So here ADC A register is given here. The start address is 7400. So that's what we have set. So ADC A start register is 7400. Now whatever settings we need to do, that we need to do in the ADC A register, that will be setting all these settings in the ADC A module, means that particular register in that ADC module, as we are going to use that particular register for our ADC sensing. So now first thing which we want to do is set this ADC control 2 register. Why this ADC 2 control register? That we'll see from here. As you can see, here it is mentioned the register ADC CTL2 has a prescale field which determines the ADC clock, and the ADC clock is used to clock the converter. So the converter which you are having here, this needs to be configured based on that. So because of that, we need to configure the ADC clock control 2 register. So here you can find all the list of the set of registers. So first we need to set this one. So you can see here we have selected our ADC A register. Now we need to configure this ADC control 2 register in that. So you see here offset is 1. So offset is 1, we key in here. So this becomes our address where we need to now set the bits in order to set the ADC to control register. So our now you can see this 7400 was address, and in 7401 if you are doing, we are now we are referring to ADC control 2 register. Now here we are moving 0008 as you can see. So as you can see here, ADC control 2 register is a 16-bit register, and if you are moving 0008, that means we are the first 4 bit are being set, and if it is 8, that means the last bit is 1. So as you can see, this means 1000 has been moved. That means input clock divided by 5. So that's what we are doing here. So we are giving 8 here in hexadecimals. So what does it do? It sets our prescale value to 8H, that is 200 by 5, and other fields are 0. So if other fields are 0, it will go to the default mode, like signal mode will be single-ended, and the resolution by default will be 12-bit resolution. So all these things are set, and the sections which where reserves are set, that we need not check. That will be by default to be set, that you can just read. Okay, so now going forward, now we have done the second step. The prescaling has been done, and in the first step we have selected the clock. Now even that in that clock we have configured the ADC control register, which has selected the resolution, the signal mode, and the prescaling value for the sampling block. Now the step 3 is powering up our ADC. So this is ADC power down block, like and this is configured by using ADC control 1 block. So as you can see here, I'll go to this. So this is ADC control 1 block that is having an offset of 0. And everything we are doing in the ADC A register, so the main start address will be 7400, and based on our requirement, we'll giving the offset and choosing those registers where we need to configure our particular bits based on our requirement. So now we need to power up our ADC. For that, we need to configure the ADC control 1 register. As we can go here, we can see it is a 16-bit register, and there, if you see, we have moved 0084. So it is to set the bit 2 and bit 7 so that interrupt first generation occurs at the end of the conversion, and all the analog circuitry inside the code is powered up. So it serves two purposes. By setting the 7th bit on, we are powering up our ADC, and by setting the 2nd bit, that we can see here, see the seventh bit is used for powering up the ADC. So if it is set to 0, it is powered down. 1 means it is powered up. So we are powering it up, so we'll set it to 1. And here is the interrupt pulse position. So that we are setting. Interrupt pulse generator occur at the end of the acquisition window, that we are setting it to that. Sorry, at the end of the conversion, not at the acquisition. So that's why we have set it to 1. So that's why we were moving 8-4. So why you can see from here, that is the third bit. So it will become 0100. So that's why 4. Now step 3 is done. Coming to the fourth step, and it's the same thing you can see in the code also. So step 3 is done. In XAR0, the 7400 offset is 0 itself. So directly in 7400 we are moving XAR0 0084. So that will set all these the powering of the circuit and the interrupt pulse position. Like each interrupt will be given after the end of the conversion that we are setting. Now the last step is, as we have done all this configuration, it needs some time, maybe very small amount of time to configure all these things and the ADC module to turn on. So we'll be writing a small snippet which will be just a delay program, so that it will get some time to turn on. So it is a small program written here, just to give some window for ADC to turn on. Moving forward, now since ADC configuration has been completed, so now we have reached this configuration has been done, everything. Okay. So all this configuration has been done for the ADC and these all things. Now this SOC configuration we need to do. Like based on this SOC configuration, all this sampling and all will take place. Like how many samples we need to sample in a particular time window, these all things, and at what time this interrupt should be generated. These all things will be done based on that. So this SOC needs to be configured. So coming to that, first again, since we are dealing with ADC A register, so the base address will be, start address will be 7400. Now in that we need to configure ADC SOC 5 control register. As in the objective itself we have told, you can use any other SOC also. You can configure any other SOC on the available SOCs, SOC 5, 6, whatever you want, to your respective ADC input. So here we are configuring SOC 5 for our this example program. So here offset you can see for accessing this ADC SOC 5 is 1A. So I'll show you here also. Like these things you can you should check, because if you want to really write a code in this one, you need to know like what is the starting address and then what is the offset, so that you can access these all things. So here you will see various SOCs are there, 16 SOCs are there. So which one we are configuring? We are configuring SOC 5. So that is 1A. Okay, now we'll go here. As you can see, it is a 32-bit register. And what options it is giving us? First one is acquisition prescale, ACQPS. The other one is channel select, which channel which we are going to use for this SOC. And another one is trigger set. So all these bits we need to set in order to configure our SOC 5. As you can see, first we need to know, like in order to set the acquisition prescale value, we need to know what is our sampling window. So here we have considered a 100 nanosecond acquisition window. So based on that, as our system clock is 5 nanoseconds, so based on that, acquisition window is around, will come around 20. And then the acquisition prescale register value is equivalent to the window time -1, that will come around 19, and the equivalent hexadecimal value is 13. So this will set the acquisition prescale. This acquisition prescale is 13, we need to set here. And the other thing is setting the trigger select and the channel select. First one, the channel select is like which ADC input which we are going to use for this SoC. So for doing that, as we have seen in the first slide itself, it is pin number 70 which we are going to use, and same thing I'll show you here. This pin number 70 is corresponding to ADC input A1, right? So this we need to configure, and the trigger select, we are using the default one. We can use any other triggers also, but make it to make the code simpler itself, we are using software interrupt itself. So we'll see how we have set these things. As you can see, here we have moved 8013 and 0. Why 2 times? Because it is a 32-bit register, and some set of these bits are in first 16 bits and others are in the later 16 bits. So here we'll see. So as you can see here, there are various triggers available. So by setting this all bits to 0, we are selecting this software only, ADC trigger to software only. So those bits are 0. Another thing is this channel select. In channel select, which one we need to configure is ADC in 1, right? So it is starting from bit 15. So in order to, as you can see, 15 to 18, 15, 16, 17, 18, 4 bits are there. So we need to set it to 1 in order to configure it to pin number 70, right? So because of that, we need to set this 15th bit, as you can see here, to 1, right? So as we'll see, set the 15th bit to 1, it will become 1000, right? Because before that we have moved 13 in the acquisition prescale value. As you can see here, the first 8 bits are set for that. So acquisition prescale, that is that we have set to 13. So bit number 9 to 14 are reserved. So only you are left with the 15th bit. So reserved means it will be 0 by default. So these are 0, and the 15th bit we have set to 1 in order to set the ADC in 1. So 1000, so 8013 has been moved. So based on this, now your SoC 5 has been configured. And same thing we'll see here. So first 7400, in that 1A, because 1A is the offset for SoC 5. In SoC 5, in the first 16 bit, we are sending 8013. By sending 8013, we are setting the acquisition prescale value, and the second thing which we are doing is setting the channel select, that is we are selecting it to the ADC input 1, and we are doing a post increment so that the next set of 16 bits we need to set for the trigger select, and by sending here there 0, we are setting it to software mode. Now after this, you have configured your SoC. Now we need to set our interrupt source selection also, and in what mode it will operate. As I had shown in the block diagram itself, like after the SoC, EOC will be produced, and that EOC goes to the input of an interrupt block, and from there ADC interrupt is generated, so that SoC will get to know like one set of conversion has been completed. Now it can proceed with the second. So for that, we need to set the source for this interrupt. Source for the interrupt is the EOC. and in what mode it will operate, that also we need to set. So as always, as we are doing everything in ADC here, 7400. Now we'll see like which interrupt which we need to use. First, I'll show you like this one nice block diagram has been given here in order to understand this thing. So here in EOC and interrupt operation, as you can see here. So here's all the 16 EOCs are there, and for each EOC we have 4 interrupts: INT 1, 2, 3, and 4. We can use any one. Okay. So same thing now we'll see in the ADC registers, and you can see here we are giving these interrupts to the. You can give it to the other peripherals. In our case, we are giving it to the SoC so that it will understand the conversion has been completed. So going to the ADC registers, as you can see here, 4 interrupts are there, right? So at a time, interrupt 1 and 2, and here 3 and 4. We want to set our interrupt 1. So for that, the offset is 7H. Here you can configure both 1 and 2, and the interrupt offset is 7H. So because of that, here 7. So now we need to set everything in 7407. Same thing has been written here. In 7407, we are moving in XAR0. Now we need to configure, like based on our configuration, we need to set these bits. So we'll go there and we'll see how it is being done. So first we need to select our EOC. As our SoC is 5, our EOC is also 5, and we are going to select interrupt 1 for that. As you can see, bit number 0 to 3 will select the corresponding EOC for the interrupt 1 selection. So this 5 we need to move there. So that is very much easy. 0, that thing 5 we can move there, right? And therefore 5 here. Then the second thing was like in which mode we need to operate this interrupt. So there you can see we need to set 6th bit for that. In order to set the 6th bit, that is enabling the continuous mode enable. What it does is like the interrupt pulse are generated whenever an EOC pulse is generated. EOC means whenever an end of conversion has been done, a pulse will be generated so that the interrupt flags will be set. Like the conversion is completed, this interrupt is active. Means whenever the conversion is going on, interrupt will be set to 1. Whenever it is completed, it will be set to 0. Right. So by setting it on, these flags are set. Based on that, we can later read whether the conversion is still going on or it has completed. These things can be read. So setting this 6th bit and 0 to 3 bit, we are configuring EOC 5 and ADC and interrupt 1 in continuous mode enablement. So we are moving 0065 to the address 7407 to select INT1 for EOC 5 and to enable continuous. Now before storing the results, so one thing we need to be clear of is that the interrupt flag needs to be cleared. Like there can be some garbage value, right? So it should be cleared before in the configuration process itself. So for that we need to see like from where we can read this. So base address is same. Now we need to see ADC interrupt flag clear register is there. So I'll show you. And we can go to the summary table. As you can see, ADC interrupt flag clear. What it does is we can clear the corresponding interrupt flag. So if we are sending 1 here, it clears the respective flag. So in 7404, we are moving 1 so that by default in the beginning it will be cleared. Same thing you can see here by doing 7404 and 001 is sent there so that it will be clear. Now, as you can see, all the configuration process has been done. Now, after this process, we have to send a signal so that the conversion should start. This SOC should start sampling. It should send signal to the sample and hold circuit, where you can see basically a capacitor where the switches are there. Those switches will be controlled and capacitor will be getting charged, and that will be given to the converter and it will give in a digital pulse. So how to do this start of conversion? So as we have mentioned, SOC 5 is being selected for this one. So for start of conversion is there. So going there, we can see again this block diagram, not block diagram, ADC base addresses registers. Now we need to set everything for this start of conversion process. For that, we need to set this particular register, ADC SOC force 1 register. So as you can see here, ADC SOC force 1 register. We'll go there. Now based on our which SOC we need to configure, like in our case, ours is SOC 5. SOC 5. So 1, we have to enable this bit so that force SOC flag bit to 1. This will cause a conversion to start once priority is given to SOC 5. So here we are doing this. So we are moving, and as you can see, it is at 5th bit. 5th bit means 020020 to address 740T to force SOC 5 flag bit to 1. This will cause a conversion to start once the priority is given. And whether the conversion has been completed or not is checked by reading the interrupt flag, as I have already told you. So if 0, conversion is in progress, and if 1, it is completed. Later the flag is cleared upon completion. So this can be read from here, 7403. So for same purpose, if you go here, in the interrupt service routine, first we are forcing the SOC to turn on. So for that 740D, there we are moving 0020. So now conversion has started. Now whether conversion has completed or not, so that I told you already, that end of conversion will act as an input to the INT1, and based on that INT1 will give some signal. So we need to read that particular interrupt. So that is 7403. So here 7403, this interrupt flag. So INT1, this flag we can read. So for reading that, we have written a small logic where we are just moving that to AH and doing some comparison. Whenever it is equal to 0, it will stay in the loop, and again it will keep on checking. Whenever it sets to 1, means conversion has completed. So it will come out of the loop. Now it will clear the flag so that the conversion has completed now. Now the final part is reading the ADC results. So as we are referring to SOC 5, our result will be stored in the 5th register. But again, now the base address will change. Earlier we are always referring to the 7400. Now for the final stage, you will see here ADC base registers. So ADC result register, it starts from 0B00. So okay. So ADC result registers, as you can see. So here we need to read which one? result 5, right? So result 5 we need to read. By default it will be 0. Just what we uh, means, it is just a reading register, right? It is reading mode. Only we can read, no need of writing. So we'll be mentioning 0B, 00 is the base, and then the fifth one we need to read, and that we can move in any register we can read, and finally for our convenience we have kept it in AR3. And all these things have been implemented. This reading part, especially this conversion and the reading part, has been kept in the interrupt service routine in the timer 0. So because in the previous I think tutorial you might have been told that all these EPWMs are implemented in the timer 0 interrupt itself. So as this data will be used for these controllers itself, so we are this reading and all part we have kept in this ISR subroutine itself. So now what I am going to do is I'll show you. So I think that's it. The PPT is, we are done. Same thing I have written here. So now we'll implement this particular code and see how it works. So I'm building it. So build is finished. I don't know whether you can see here. I have used this 3.3 volt pin which is available here, that itself, and I have configured it for this pin number 70. Okay, so now I'll be giving this reading all these things in our CCS. On reading, processing, run. As you can see, our final result should come in AR3 register, right? AR3. So refreshing it. I think I need to close it and again open it. Fresh. So as you can see here, XAR3 FFF has come. So now I'll change this input. Now I'll try to read 0 volt. You can do the same by connecting it to the ground pin. So now I'm connecting it to the ground pin. It should show 00 instead of FFF. Now if we'll see here, it's showing 0 now. Okay, now again if I connect to 3.3 volts, it will again show FF. See, triple F is coming. So you need to take care of this refresh. Sometimes it doesn't work. You need to close this register bar and again open it. So that way, I would recommend you can use any other ADC input also. Like I'll show you here. In this, like I have done for pin number 70, you can set pin number 30 and check. For that, you need to configure ADC input A0. So okay, I hope this is informative for you. These were the references, these modules. So these already have been given to you. So go through it and try to implement it. It will be very much nice for you. So okay, thank you.